Well, good morning, everyone. Thank you for coming to my presentation. My name is Steve Donaldson, and I'll be speaking this morning on Petro-Lithium resources of Western Canada, the state of the basin. Here's the typical boilerplate disclaimer. No, I'm not going to read all of it. So this is the outline of my presentation. I'll begin by introducing critical and strategic minerals, their definition and their importance. I'll follow up with a discussion about lithium, its properties and uses, past, current, and forecast demand, global production and sources. So who is producing it, where are they producing it, and how are they producing it? Then I'll move on to talk about Petro-Lithium within the WCSB, the data that's available, where the lithium originates, and its geological setting and fairways. Then I'll go on to talk about the recent history of Petro-Lithium exploration in the WCSB and current operator activity. Then finally, I will talk about my summary and conclusions. So this is Canada's critical and strategic minerals list. It was released on March 11th of this year. And this list comprises 31 minerals, all found in Canada. These minerals are essential to Canada's economic security, required for Canada's transition to a low carbon economy, and a sustainable economic source of critical minerals for our international partners, such as the United States, the European Union, the United Kingdom, Australia, Japan, and South Korea, which may need these minerals for their own economic and national security reasons. This list includes minerals used in various strategic industries such as clean energy, consumer electronics, critical infrastructure, agriculture, advanced manufacturing supply chains, and defense. The consumer applications of these critical minerals include batteries, solar panels, permanent magnets, and wind turbines. And sitting right there is lithium. Just a quick overview of this element. There's its chemical symbol. It is the third element on the periodic table. It's classified as an alkali metal. It's low density and lightweight. In fact, it's the lightest of all metals. Has a high specific heat and a high thermal conductivity, a high electrochemical potential, and typically occurs in nature as lithium salts, like lithium chloride, or as a component of minerals such as spodumene. These properties make lithium useful in many industrial and high-tech applications. So here's an interesting diagram of lithium use by sector and how it's changed over the past 10 years. So lithium is used in the creation of rubber and plastics, pharmaceuticals, added to aluminum as an alloy to decrease weight and improve strength in aerospace applications. It's also used in air treatment to provide cooling, remove carbon dioxide, and control humidity. It's used as a thickener in many lubricating greases and also in making heat-resistant ceramic and glass. Think of your glass stovetop as an example of the latter. Most importantly, though, it's also used in the manufacture of batteries, including lithium-ion rechargeable batteries. If you look at these diagrams here, on the one on the left from 2010, lithium use in batteries accounted for 23% of the total use of that element, whereas back in 2020, just a year ago, that had more than tripled to over 71%. So it's obviously an increase in rechargeable battery demand that is driving lithium consumption today. Here's the same thing shown in a slightly different way. It's this ever-increasing demand for rechargeable lithium-ion batteries for consumer electronics, power storage, and transportation that, no pun intended, continues to drive current and future demand. Here we are looking back to 2011, to the current year, 2021, and then forecast increase in demand in terms of gigawatt hours per year up to 2030. And this is because of the need to increasingly limit CO2 emissions worldwide. So lithium-ion rechargeable batteries are used increasingly in the transportation sector. And as you can see from this chart, it's mainly passenger and commercial electric vehicles. These are the main reason for this increase. So who's producing all of this lithium and who contains most of the reserves? You can see that most lithium production and the majority of reserves are held by Australia, Argentina, and Chile, and I would actually add Bolivia in here. Argentina, Chile, and Bolivia form the so-called lithium triangle of South America, and China is also a contributor. There's no current significant lithium production from North America. This means that supply chains are quite long when they're needed to supply minerals or materials to manufacture rechargeable batteries. And from these sources around the world, it comes from, there are four main methods of extracting lithium from the earth. Number one is hard rock mining of spodumene, lithium pyroxene from pegmatites in places like Australia and China. Salars or salt lakes, as I mentioned, from Chile and Argentina, the lithium triangle, as well as China as well. Lithium clay-rich minerals are known to occur in the United States. And last but certainly not least are oilfield brines. This is Petro-Lithium from places like Canada. Running down this list, if we look at hard rock mining and pegmatites, lithium occurs in conventional ores, primarily as spodumene, lithium pyroxene, in pegmatite deposits. These are medium to large size deposits confined to the unweathered extent of the ore body underground. They typically contain the highest lithium concentrations of the four sources. And these are just typical drill and blast, so heavy machinery is used to excavate them, making them energy intensive and expensive to extract. There's also the use of chemical reagents for refining. Lithium from salars or saline lakes. So this is the extraction method used in the lithium triangle area of South America. These are large deposits with lithium in solution as a brine at very shallow depths. The lithium chloride brine is pumped to the surface into evaporation ponds, as you can see here in the picture, where it's concentrated by evaporation in the arid climate, because it is the Atacama Desert after all. This is an inexpensive but slow process, taking 1.5 to 2 years to concentrate the lithium. There are also local concerns regarding freshwater use for this process in such a dry region of the world. Lithium can also come from clays. This can be considered somewhat of a hybrid deposit, where the hectorite clays are ore, and hectorite is simply a lithium-rich montmorillonite or smectite, a swelling clay. Heavy machinery is used to excavate the clays via surface mining. Ponds are then used to leach and concentrate the lithium chloride. These are typically small to medium-sized deposits, and these are still in the early stages of commercialization. Last but not least is Petro-Lithium from oilfield brines. These are deep unconventional brine resources, unlike the shallow South American salar brines. They're extracted via wells from high-rate, high-water cut, end-of-life oil and gas reservoirs. So this produced brine becomes a revenue stream rather than a waste product that has to be disposed of. These are lower cost and less energy intensive than hard rock mining, and direct lithium extraction allows faster processing than lithium sourced from salars. This is also a great opportunity to leverage both existing oil and gas infrastructure and a very experienced workforce that currently exists in Western Canada. It's a win-win, really. So in the Western Canada Sedimentary Basin, we have a bit of a history of lithium exploration. A wellhead brine sampling program was conducted by both the AGS as well as the Saskatchewan Geological Survey from the 1990s through the present day. These sampling programs provide information about concentrations of lithium, as well as other trace elements broken out by location and formation, or depth. This extensive data set is available within the public domain, although Alberta has more data as sampling commenced earlier than in Saskatchewan. As required by law, public Petro-Lithium operators submit NI 43-101 technical reports containing data from their own wellbore sampling programs. These are also publicly available. And the data set for Alberta is much more extensive than that for Saskatchewan, as I said, because it had started earlier, but this is both in terms of number of wells sampled and number of stratigraphic intervals sampled. So when we plot this up, this is what we get. Just to orient ourselves, this is the Western Canada Sedimentary Basin through BC, Alberta, Saskatchewan, Manitoba. There is no data from Manitoba. The brown line here is the erosional edge where the basin onlaps the Precambrian shield. Here's the deformation front in the west. And these are the lithium concentrations. The coolest colors, the dark blue, are where the lithium concentrations are the lowest. The warm colors are where the lithium concentration is higher, and red is the highest concentrations of all. There are some other structural features on here. Here's the Bow Island Arch. Here's the Peace River Arch and its axis going that way. There's also Leduc Reefs, Slave Point Reefs, and Swan Hills Reef complexes on the map. You can see the colors. This is the salt collapse edge of the Prairie Evaporite Formation, and these are erosional edges of other formations within the Williston Basin. When we plot this data up stratigraphically, there it is areally, but when we plot it stratigraphically, we find that it's the Devonian strata that have the highest concentrations, namely the Beaver Hill Lake group, which is the Swan Hills and Slave Point formations, the Woodbend group, which is the Leduc Formation in Alberta, and the Duperow Formation in Saskatchewan, which is its equivalent, as well as the Wabamun group and/or formation. And we find specifically that a lot of these highest concentrations are also associated with some of these Devonian reef buildups, as you can see here. So Eccles and Berhane in 2011 put together a schematic model for lithium mobilization into these Devonian aquifers in West-Central Alberta, specifically the Fox Creek area. And they surmised that lithium mobilization and enrichment is associated with alterations of silicates, in other words, lithium and potassium-bearing minerals within the Precambrian basement. Then you are either getting direct contact between Devonian waters and this basement, or mobilization of silicate-bearing fluids into the aquifer aided by deep faulting. They saw a positive correlation with dolomitization as well within the carbonate units. And there's a speculated genetic association with underlying Precambrian terranes and terrain boundaries. So just to orient yourself, the gray here is the Precambrian basement. It's uplifted in the Peace River Arch, PRA. These are the immature lower Paleozoic clastics, Cambrian sandstone and granite wash, the Gilwood member, and basically the lithium is coming up through faults and tectonic zones within the Precambrian. It's going upwards into the limestone where dolomitization is occurring, and you're getting lithium enrichment within the pore waters of these Devonian reefs. So here's the Peace River Arch outlined in a nice bright red circle. So these areas of elevated lithium concentration may correspond to areas exhibiting significant deep faulting, like the Peace River Arch, which is fault bounded. Deep-seated faults provide a vertical migration pathway from Precambrian lithium sources into overlying carbonate reservoirs. And as I just mentioned, permeable clastic wedges shed off the arch could also provide pathways for fluid mobilization. If we look at an aeromagnetic map of some of these Precambrian terranes, there's a lot of them. I've labeled just a few that were mentioned in Eccles and Berhane. If you overlay lithium concentrations on the Precambrian terrain boundaries. This also shows a possible, though somewhat speculative, correspondence with the fault-bounded edges of the Chemawan isotopic anomaly, which is a feature in the Precambrian basement, as well as the snowbird tectonic zone, which comes through here. So it's sort of the confluence of these areas that are fault-bounded. And in the case of the snowbird tectonic zone, this edge here is actually a shear zone. Both of these could have provided basically faulted pathways for that lithium to make its way from the Precambrian basement up into the Devonian reservoirs. So this map shows the disposition of metallic and industrial mineral rights held by operators in BC, Alberta, and Saskatchewan. Not all companies were able to be specifically identified, but the majority of these will be Petro-Lithium operators. The identified companies on this map include those who have been around for a few years, as well as some newer players. I mean, here's E3 in the red, E3 Metals, Prism Diversified. They've been around for a few years. There's also new players in the game, companies like Highwood, as well as Prairie Lithium. So if you'll pardon the horrible pun, these are the operators that are leading the charge in the search for battery metals. Haha. And if I do this, you'll see that where they picked up the metallic and industrial mineral rights for lithium is, and it's no surprise, this is where the highest concentrations of lithium are occurring around these reefs. Just a word about these mineral rights. They're required slightly differently in each province. In Alberta, these resources, along with those of superficial deposits such as sand and gravel and any mineable substance, with the exception of oil sands and coal, are included under metallic and industrial mineral rights and must be obtained separately from petroleum and natural gas rights, even if they are hosted within an oil and or gas producing geological zone. Similarly, in BC, they are referred to as mineral and placer rights. In both Alberta and BC, these rights are obtained via applications made directly to the Crown for specific areas. There is no bidding process as with PNNG rights. The only restriction beyond the payment of application fees is that the rights in question not already be under disposition. Once obtained, metallic rights are maintained through rental fees and work requirements. In Saskatchewan, rights to brine minerals are included under subsurface mineral rights and are also separate from PNNG rights, but have been granted via a competitive bid process since December 2018. Rights are posted 3 times a year in April, August, and December. And Manitoba is not currently engaged in any development of Petro-Lithium resources. So I had mentioned direct lithium extraction a bit earlier in the talk. Although these DLE processes are proprietary, they will likely be based on one of these 3 methods, either adsorption, ion exchange, or solvent extraction. The adsorption process typically adsorbs lithium chloride molecules onto the surface of a sorbent from a lithium-loaded solution with water as a potential stripping solution. This is sort of analogous to a sponge soaking up water or whatever sort of a mess there is and then squeezing the sponge to get rid of it. The second one, ion exchange, takes lithium ions from the solution by trading lithium ions for protons or other cations within the sorbent's structure, which is the blue thing here, the dark blue. An acid solution is typically required for stripping and recovering the lithium from the sorbent afterwards. This is sort of analogous to maybe water softeners that a lot of us may have in our water systems at home. The last, solvent extraction, exchanges lithium chloride molecules or lithium ions between brine and an organic liquid phase containing an extractant that complexes with lithium or lithium compounds in the brine. To be successfully deployed, direct lithium techniques must be able to extract lithium from complex brines with high concentrations of other ions, such as sodium, potassium, calcium, magnesium, borates, and sulfates. So, summary and conclusions. As I've mentioned, lithium's unique properties make it an essential component of industrial and high-tech industries. Increasing demand for lithium is forecast as a result of global decarbonization policies and the move to lithium-ion batteries for transportation. Lithium production is currently dominated by foreign sources with long supply chains. There is a need for a reliable domestic supply of lithium. The WCSB hosts abundant lithium resources as Petro-Lithium, predominantly within oilfield brines of Paleozoic age reservoirs. Multiple operators have acquired metallic and industrial mineral rights in BC, Alberta, and Saskatchewan to develop this resource. Direct lithium extraction for many operators is currently undergoing laboratory testing and field testing. This is one of the last major hurdles before full-scale commercialization of Petro-Lithium. Lithium is known as white gold, so I leave you with the idea that the white gold rushes on. Acknowledgements to Canadian Discovery and the following CDL staff in particular for their technical assistance and critical feedback during preparation of this presentation. I'd like to thank you all for your attention during my short talk here this morning. Please, while there's still time, drop by our virtual booth to pick up your copy of our mini digest poster featuring Western Canada plays. As well, the presentation I've just provided you will be available to download on our website. We also have a much more in-depth version of this presentation that we'd be happy to do for your company. Please contact our sales staff. Here are some contact details for myself, Meredith Faulkner, our Technical Analysis Director, Kaush Rakit, our CEO, and our two sales staff, Adam Starulia and Krista Williams. Thank you very much for your attention.